So, last class I have discussed that how I will design a isolated footing on sand, and based on the n values for different depth that was given. So, this is the problem that was given, that determine the net allowable bearing capacity of pressure of a square footing of size 3 meter cross 3 meter resting on sand with the following properties. And water table location was 2.5 meter from the ground surface, depth of foundation was 1.5 meter, permissible settlement was 50 millimeter, and the factor of safety against bearing was 2.5, and this is the n values were given. So, from the bearing capacity consideration, we got net safe bearing capacity was 515 kilonewton per meter square. So, that was the net safe bearing capacity we are getting, and we got, and this is in terms of bearing consideration, bearing capacity or bearing consideration, and for the settlement consideration, so we are getting that for the width of foundation is equal to 3 meter, and we have the n average is 27, and corresponding settlement so from the chart was 10 to the power minus 2 meter for 1 kg per centimeter square. Okay. So, or we can write in terms of millimeter 10 millimeter for 1 kg per centimeter square, or I can write that for 1 kg per centimeter stress, the amount of settlement is equal to 10 millimeter. Okay. Or I can write for 100 kilonewton per meter square, that is for 1 kg per centimeter square is equal to 100 kilonewton per meter square. Stress, the amount of settlement is 10 millimeter square. Okay. So, this was the case we finished in the last class. So, now from here we will start the other things, and then what we will do that we will go for this chart. So, this chart we know, and from this chart, so our it is given that for 100 kilonewton per meter square stress, the amount of settlement is 10 millimeter. Okay. But there water table effect was not introduced, but here water table is 1 meter. So, water table is 1 meter, if this is the water table. So, water table is 1 meter below the ground surface, because water table not below the ground surface, water table is 1 meter below the base of the footing or 2.5 meter below the ground surface. So, 1 meter below the base of the footing. So, here you can see, so you have to use this chart. So, here there is a term d by b. So, this is the water table depth from the base of the footing. In other case, we are using dw dash. So, that dw dash here d both are same. So, remember that in these problems we are using different notation in different cases, and because these are the chart, this has been developed this way. So, we have to use those notations only, but I am explaining that what are the similarity of the notations, what are the difference between these notations. So, here D or dW dash both are same. So, if this is the D by B, so we have to use this chart. So, here D value is 1, B value is 3. So, okay. So, again from here, so if this is the again this value is coming out to be again this is 0.65. So, W dash is 0.65. Okay. So, this is the similar chart we use for the bearing capacity purpose also. So, but here it is given the similar kind of chart, in different way it is been represented. So, but we have to use them and you should know what are the meaning of different notations. Okay. So, similar chart here also it is 0.65, previously also it is 0.65, that R W dash was 0.65 for the bearing consideration. Here W dash, because they are R W dash, here W dash, both are same. So, but you have to use, you should know how it is been used, because in different way it is been used. So, that means this is the W dash is giving 0.65. So, now your actual settlement, because this is a settlement computed from the SPT value. So, the actual settlement will be settlement computed from the SPT value is 10 millimeter and the correction factor is 0.65. So, as I mentioned, for the settlement you have to divide with the correction factor, because then it will increase the settlement. Okay? Because in the settlement water will always create a negative effect. So, and for the bearing you have to multiply with this correction factor, because bearing capacity will be reduced because of the water table rise. So, this is the 10. So, that means our settlement is 15 point actual settlement 4 millimeter. So, for 100 kilonewton per meter square stress, the actual amount of settlement is actually 15.4 millimeter. Okay. So, but your permissible settlement is 50 millimeter. So, you are getting 15.4 millimeter settlement for 100 kilonewton per meter square stress. Then the question is, what would be the stress for which you will get the 50 millimeter settlement? So, that stress will be your allowable stress in terms of, or safe bearing capacity in terms of settlement. Okay? Because we are getting 15.4 millimeter settlement for 100 kilonewton per meter square stress. So, what would be the stress I will get a 50 millimeter settlement? So, that stress will give me the safe bearing capacity in terms of settlement. So, the Q ultimate or Q safe in terms of settlement will be equal to that we are getting for 15.4 millimeter settlement for 100 stress kilonewton per meter square stress, then 50 millimeter settlement for which stress. So, you will get this is 100 divided by 50 into 15.4. So, that is given 324.7 kilonewton per meter square. Okay. So, this is the stress safe bearing capacity that I am getting in from the settlement consideration. Okay. So, that means we have two stresses now, one is from the settlement consideration, one is from the bearing consideration. So, if I now go for this our problem, that for the bearing consideration, Q net safe is 515 kilonewton per meter square, and Q safe for settlement consideration is coming out to be 3 to 4.7 kilonewton per meter square. So, minimum of these two because this is the maximum stress the foundation can take in or soil can take in terms of bearing capacity, and this is the maximum stress the foundation can take in terms of settlement consideration. So, minimum of these two will give you Q net allowable. So, this Q net allowable will be 3 to 4.7 kilonewton per meter square. So, this is the net Q allowable. Now, one thing is that so this is we have considered the bearing and settlement separately, then based on that we calculate these things. Now, there as I mentioned in the last class that we can use directly the N value to calculate the net allowable bearing capacity directly. Here we are getting the net allowable bearing capacity based on settlement and the bearing consideration, but directly we can also get the net allowable bearing capacity by using the expressions based on the N value. So, I have given 3 expressions. So, I am using the first one, and let us see what is the, because those values are given. So, if I use the Peck, Thorbern and Hansen and Thorbern expression, so that will be given. So, I can use if Peck, Hansen and Thorbern, which is given 1974, their expression is Q allowable net or net allowable is equal to 0.044 Cw NSA. Okay. So, this is in ton per meter square. N is the average N value, S is the permissible settlement, and Cw is given is equal to 0.5 plus 0.5 into dW divided by dF plus B. What is dW? Again I am writing that this is the position of the water table, which is 1 meter below the base of the footing. This is dW, which is 1.5 meter, and so dF, this is dF 1.5 meter, this is dW, sorry, the dW is from the ground surface. So, dW value is from the ground surface. So, dW will be equal to 2.5 meter. So, I can get Cw is equal to 0.5 plus 0.5 into dW is 2.5, dF is 1.5 plus B is 3 meter. So, this is 0.78. Okay. So, now if I put this value here, this is 0.044, Cw is 0.78. In here, which one we will consider? Here I will consider the twice B part, because here both settlement and the bearing is considered. So, we have to take the influence zone as a twice B. So, if the influence zone is twice B, then my N average value is 27. So, we have to take the 27 and the permissible settlement, because my n average is 27 and A is the permissible settlement, is equal to 50 millimeter. Okay. So, I can write this is 50. So, this value is coming 46.332 ton per meter square. This is 46 point, or it is 463.32 kilonewton per meter square, because your 1 ton per meter square is equal to 10 kilonewton per meter square. So, if I directly calculate this thing, so it is giving 463. So, now we compare these two, directly we are getting 463 and from the settlement consideration we are getting 324.7. Here also it is, because here two different approaches we are using. So, now so from here ultimately I will use, this is my load carrying capacity or the net allowable bearing capacity, because that is given the lowest. Okay. Now, and so that means that finally, I will provide the Q net allowable will be equal to 324.7 kilonewton meter square or 325 kilonewton per meter square. So, this is the final recommendation based on we are getting. Okay. So, here based on the available data, I have used the SPT value correlations, those are given. So, based on I have directly calculated, I have calculated in terms of bearing, I calculated in terms of settlement, that from there the minimum value I am getting. So, in the assignment or your exam, it will be given that whether you use the directly this expression, or if nothing is mentioned, then you use all these methods and then get the allowable bearing pressure. Okay. So, this is the, so now based on that, now it is this is your dimension of the foundation. Now, you can get what would be the amount of load will come. So, finally, the I can say that Q allowable, this is the load. So, this will be your 325 into the area is given 3 cross 3, this is the 3 cross 3. So, that is the kilonewton will be your the Q allowable. This is the load the foundation can take. So, your foundation, this foundation can take this much of kilonewton load, that is why your bearing will be, there will be no bearing capacity failure, and the settlement is also within the permissible limit. So, this is the final recommendation that are given. So, this is the design load that you have to design your foundation. So, you have designed your foundation. So, this is the maximum load you can apply as a design load on the foundation. So, that means we have here we have first fixed the dimension, then we recommend the design. In other way also you can do it, that you have the load is given, you can choose the dimension, because in that case it will be a trial and error process, because first trial you choose a dimension, if it is satisfying all the criteria is fine, then you go for the next, if it is not satisfied, then you go for the next dimension. So, here as I mentioned, so I will give you the how to you will calculate the dimension of a foundation or depth of foundation. So, in your design part. Okay. So, this is the design of a isolated footing resting on sand, and we have designed it based on the n value, because in most of the and it is on the sand. So, based on the n value we have designed it. So, in the next part that I will discuss, I will design a isolated footing which is resting on clay. Okay. Here it is on sand, Next one, I will go for a isolated footing which is be resting on clay, and then I will design a raft foundation which will be also resting on clay. Okay. So, here also if it is a raft foundation, then also you can do it for the sand, but here and 50, why I have written 50, because for the RCC in the permissible value RCC on sand or hard clay, the isolated footing, the permissible settlement value is 50 millimeter. So, that is why I have taken permissible settlement value as a 50 millimeter. Okay. So, the next problem that I will discuss, that foundation isolated footing on a clay. So, these are typical columns of a total building. So, what is isolated footing? If I design foundation for a individual footing. So, there is a possibility that two footings may come overlap. So, in that part I will go for the combined foundations. The combined foundation can be rectangular, combined foundation can be trapezoidal depending upon the requirement, and if I take all the columns in one foundation, then that will be the raft foundation. So, first problem that I will go for, it is for the problem. So, design of isolated footing which is resting on clay. Okay. So, we are designing, suppose as mentioned that we have, say, this is the location of a column of a building. This is the column location. So, we are going for a single footing for each column, and we are saying, and we are getting that this is sufficient, there is no overlap. Suppose first we try it and then see whether there will be overlap or not. If there is overlap, then we have to go for the raft foundation. So, first we are getting a center column, we are getting where the load is coming, say 600. So, in the center column load is coming 600 kilonewton. Okay. So, that load is coming. So, we are going for a isolated, we have decided that we will go for a isolated footing. Okay. So, let us the footing for each column. So, the what we are doing, that I do not know, here in the last problem that I have solved on sand, there we knew the dimension of the footing, and based on that we recommended what will be the permissible load on the foundation. But here we are doing the other way. You can do that, you can solve that problem also in other way, but it is in different way. I am showing that so that you can do it in different way also. Here I know the load, and I have to design the foundation according to that load, okay, and based on the available soil properties. But it is on the clay. So, that in the amount of load that is acting is Q is 600 kilonewton. Okay. And we are assuming that this load because this 600 kilonewton is including the footing weight. If the footing weight is not given, it is only the load coming from the superstructure, then you have to the weight of the footing also you have to add. Okay. But here we assume that this Q is including the footing weight. Okay. So, now this is the GL ground level, so this is ground level, and the depth of footing I do not know, because you have to decide, and so that means location of water table is at minus 2 meter. This is the location of water table, 2 meter below the foundation, 2 meter below the ground level, and we have 3 layer soil system. So, this is the first layer which is minus 4 meter, then the next layer which is minus 6 meter, this is the another layer which is minus 10 meter. Okay? And this is the depth of foundation, I don't know, but for the first trial what I have taken, that I will place the foundation at 2 meter below the ground level. So, for the first trial I have taken, so df is taken or chosen as 2 meter. Okay? Because so that in all the soils is the silty clay. Okay. All the soils are silty clay with different properties. So, properties are given, the Cc 1 plus E 0 is equal to given 0.07, then unit weight of water is given kilonewton per meter cube, 18 kilonewton per meter cube. Cu value is given 30 kilonewton per meter square, and E value is given, elastic modulus of the soil 18,000 kilonewton per meter square. This is for the layer 1. So, layer 2 again Cc plus 1 plus E 0 is your 0.15, then unit weight of the soil is 19 kilonewton per meter cube, this is 19. Cu value is given 50 kilonewton per meter square. Sorry, this is Cu value is given, here it is 30, here Cu value is given 20 kilonewton per meter square, and E value is given 12,000 kilonewton per meter square. For the third layer, Cc 1 plus E 0 is given 0.12, unit weight is given again 19 kilonewton per meter cube, Cu value is 50 kilonewton per meter square, and E value is given 30,000 kilonewton per meter square. Okay. So, here I have decided for the first trial that I will take the df as 2 meter, and the dimension of the isolated footing is taken 3 cross 3 meters. So, it is a square footing where b is equal to L equal to 3 meter. Okay. So, this is the trial 1. So, let us see whether it is safe or not. Okay. So, that means here these 3 are assumed value. For the first trial. So, the 600, so 600 kilonewton is the total load including the footing weight. So, my Q net load that is acting on the foundation is will be 600 in divided by 3 cross 3. So, this will be 66.7 kilonewton per meter square. So, first we will do the bearing capacity calculation. So, first we are seeing whether it is safe in bearing capacity or not. So, we are doing bearing capacity. Okay. Bearing capacity. So, as this foundation is resting on clay only, so we have discussed about number of bearing capacity expressions. We have discussed Tazaki's bearing capacity expression, Meyerhof bearing capacity expression, Hanson's, Vesic and IS code, and but we have also discussed bearing capacity expression which is Skempton bearing capacity expression, which is specifically can be used for the clay. So, I will use the Skempton bearing capacity expression here, but you can use the other bearing capacity expressions also. You can use the Tazaki, but here I will use the Skempton because it is specifically proposed for the clay, and this is the only clay soil. So, the Skempton bearing capacity Q net ultimate is CNC or the CUNC. This is the Skempton bearing capacity expression. Okay. So, NC value I will get by for the rectangular footing is 1 plus 0.2 B by L into 1 plus 0.2 dF by B. So, that can be converted per square footing if you put B equal to L. So, here B is equal to L. So, if you put B equal to L, so this expression becomes 6 into 1 plus 0.2 dF by B. So, which is the expression for the square footing, and so that means here we are taking that 6 1 plus 0.2 dF is taken as 2 meter and B is 3 meter. So, it is coming out to be 6.8 and 6.8. So, which is not greater than 9. So, it is okay, because that value should not be greater than 9 if for the square footing it is recommended. So, it is not greater than the 9. So, it is okay. So, now what we will do, so that that Cu value we are taking as the average Cu value, okay, because here 3 layer soil system, and for this is for the first, here is 3 meter. Okay. So, for the bearing we are talking about, for the bearing the influence zone will be 3 meter. So, influence zone will be 3 meter. For the first layer thickness is, this is 2 meter, below the base of the foundation it is 2 meter, this is also 2 meter. Okay. But our influence zone is up to 3 meter only. So, for the bearing, so Cu average Cu value or weighted average Cu value will be that your first layer 30 into 2 meter plus second layer 20 into 1 meter, because influence zone is up to 3, second layer, and this is divided by 3. So, Cu value is coming out to be 26.67 kilonewton per meter square. So, finally, Q net ultimate that we are getting is Cu is 26.67 and NC is 6.8. So, that value will be equal to 181.33 kilonewton per meter square. So, this is the net allowable and net ultimate bearing capacity, and the stress is coming is 66.7 kilonewton per meter square. Okay. So, the factor of safety will be the Q net ultimate divided by Q net stress that is acting. So, 131.33 divided by 66.7, which is equal to 2.7. Okay. So, which is greater than 2.5. So, my design is safe. Okay. So, this is safe against bearing, but we have to check whether this is safe against settlement or not. Okay. So, we have checked it, and the dimension that I have taken. So, so this dimension footing it is safe against bearing, but we have to check it whether it is safe against settlement or not. So, in the next class I will check this dimension whether it is safe against settlement or not, and then we will provide the final recommendation of this dimension of this shallow foundation. Thank you.